Trig functions, they just keep going on and on and on and on. Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. I'm David, and today we are delving into the wild world of trigonometric functions. But never fear, dear viewer, for they're not as hard as they look. A quick disclaimer here, I'm going to be using radians throughout this video for my input into our trigonometric functions. We could be using degrees, but radians tends to be an easier and more useful measurement to input into our trigonometric functions. In general, degrees and radians are the same thing. They measure angles in a certain way, but radians are unitless, which makes them really useful. The conversion factor between degrees and radians is this. For every pi radians, we have 180 degrees. So if you ever need to convert between degrees and radians, or when I say radians into something more familiar in degrees, all you need to do is multiply by this conversion factor, or its reciprocal, 180 degrees for every pi radians. Trigonometric functions form the family of functions that have certain cyclical or repeating behaviors. You may have encountered trig functions in geometry class where we talk about them in terms of triangles, SOHCAHTOA if you remember, but it's hard to talk about trigonometric functions without getting into, say, circles. There's so much more than triangles. You may be familiar with the unit circle, but all it is a circle of radius 1 centered at the origin, and from this circle we can define sine and cosine. If I swing an angle up from the positive x-axis and draw a line from the origin to a point on a circle, the unit circle, with that angle, I can define the x-coordinate of that point as the cosine of the angle. Similarly, the y-coordinate of that point is the sine of that angle. Taking this a step further, let's build the graph of the sine function from the unit circle. Let's let our output be y, but hold on to what our input actually is for a second. Now remember that y is equivalent to the sine of that angle from the unit circle. And if we just look at this on one dimension, then the y-coordinate just bounces between the values -1 and 1, -1 and 1, -1 and 1. But that's just in one dimension, so let's branch this out into 2 dimensions. So let's determine what our input must be. Let's define our input as time, t. So if I take this one-dimensional y-axis and stretch it along time, I get this graph here. Now that's pretty cool. That is the graph of our sine function. Now I chose this input time, t, just to illustrate a point, but the input into the sine function can be anything. It could be t, it could be theta, it could be x, anything we want. From now on, I'll be using x. We can build the cosine function similarly. It looks like this. Notice that if I shift the sine function a certain amount to the left or right, I actually get the cosine function as well. So that distance between cosine and sine is actually pi over 2, or 90 degrees. So if I take the function sine of pi over 2 minus x, I actually get the cosine function. Sine and cosine are sometimes called co-functions of each other because of this property. If I shift sine, I can get cosine, and if I shift cosine, I can get sine. Now this just tells us that sine and cosine basically do the same thing, but it can be useful to use cosine in some instances, and it can be more useful to use sine in other instances. For instance, we can see that the sine function has a value of 0 at x is equal to 0. So if we have a relationship between two variables where they both should be 0 at the same time, then maybe we want to start with the sine function. Likewise, we can see that cosine starts at a maximum or a minimum in certain cases, and if a relationship between two variables starts at a maximum when the input is at 0, then we might be better off using cosine in that case. So trigonometric functions are functions that are periodic. They have a set period or interval of x values along which the y value oscillates. The average of the maximum and minimum y value is something called the amplitude. Trig functions also have a midline or an equilibrium line about which the y coordinate oscillates. And they also have something called a phase shift or a horizontal shift of the starting point of the function. Sine and cosine look like this in standard form. I have sine written here, but this works just as well for cosine. And sometimes you'll see d here instead of k. Like our other functions, all of these constants, a, b, c, and k, have some specific meaning for the function graphically. The absolute value of a, for instance, is the amplitude of the function. A is also the scaling factor, or the vertical dilation of the function. It also dictates whether the function will be flipped across the midline if a is negative. So for instance, for sine, if it once rose above the midline, it now dives beneath it. And for cosine, if it once had a maximum above the midline, it now has a minimum. B is our horizontal scaling factor, and it is also related to our period. The period can be defined as the distance between any two consecutive crests or troughs of the trigonometric function. As such, b can be equated to t in this way. So b is equal to 2 pi over t, where t is the period. This relationship holds for both sine and cosine. C is called our phase angle. More useful, however, is the phase shift, which is the horizontal shift of the starting point of the function. So for instance, for sine, since sine sort of starts at 0, 0, if I have a phase shift of pi over 2, that is going to shift the function over by pi over 2 units. The phase shift is related to the phase angle by this relationship. H, the phase shift, is equal to negative c over b. Now, of course, since these functions oscillate infinitely in both directions, there isn't really a starting point for any one of these functions, but sometimes looking at what happens on the y-axis when x is equal to 0 is a good place to define a quote-unquote starting point of the function, or a starting point of one cycle of the function. Finally, k, like with our other functions, is just the vertical shift of the function up or down. It also represents the midline of the function, where the midline is equivalent to y is equal to k. Defining the domain and range of sine and cosine, the domain of sine and cosine is just all real numbers. I can plug anything into these functions. And the range of each of these functions is k minus the absolute value of a to k plus the absolute value of a. For our parent sine and cosine functions, this is equivalent to a range of -1 to 1, both inclusive. The end behavior for both these functions is actually undefined. Since they oscillate between -1 and 1 infinitely, they never get to any specific value at infinity or at -infinity. Okay, so let's move on to our final normal trigonometric ratio, tangent. Tangent is a little bit different than sine and cosine, but it can be related to sine and cosine by this ratio. Tangent is equal to sine divided by cosine. Now, because cosine can be 0, which means our denominator of the tangent function can be 0, well, that means that this function is undefined at certain places. In fact, it's going to be undefined at every odd multiple of pi over 2. So -pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, etc. At each of these points, we are going to have a vertical asymptote. As you can see, the interval between each of these vertical asymptotes is pi. Pi over 2 minus -pi over 2 is equal to pi. So the period for the tangent function is pi, unlike for sine and cosine, where the period is 2 pi for the basic functions. As you can also see, the tangent function grows from -infinity to +infinity every cycle. So it doesn't have an amplitude like with sine and cosine. The tangent function can be written in this standard form, very similar to sine and cosine. Now, a is no longer our amplitude, but it is still the vertical dilation or scaling of the function. B is again related to our period and also the horizontal scaling of the function, where b is equal to now to pi over t instead of 2 pi over t, where t again is the period of the function. C again is our phase angle, which is related to our phase shift h, such that h is equal to -c over b. And now remember, h is the one that's a little bit easier to use. That is specifically the horizontal shift of the function. Finally, k is our vertical shift, like it normally is. It shifts the function up or down, and since there isn't really a midline to this function, there is a line of symmetry across the origin here. So we can say, what is the shift of the origin point up or down based on k? The domain of the tangent function is all real numbers except for these regular intervals of odd multiples of pi over 2. So we can say that the domain of this function is all real numbers x not equal to 2n minus 1 times pi over 2, where n is any integer. Okay, at least the range is easier. It is simply all real numbers. Next time, we'll take a look at this example problem, the infamous Ferris wheel problem. Suppose you have a Ferris wheel of radius 30 meters that rotates once every 3 minutes. If the center of the Ferris wheel is lifted 35 meters off the ground, what is the height of a passenger 2.5 minutes after that passenger got on at the bottom of the Ferris wheel? Try it out yourself, and I'll see you in the solution.